Good morning, year 10s. How's it going, everybody? Right, guys, last lesson of electrolysis. I'm going to be looking at electroplating today. Did Jack make it? No, he didn't. Killister beat him. Oh, I should not laugh at that, but it's really funny. Jack, I'm so sorry. Callister keeps beating you. You need to have words, definitely. Wait, what? Oh, that's really cracked me up. Right, okay, I've popped out the chat window. My microphone's all up and running. So, let's share screen and crack on, guys. So this is the last lesson of electrolysis, everybody. Ange. Hey, Ange. We're doing electrolysis, Ange. You're more than welcome to join us. Ange is one of my AS students, by the way, guys, and he's a very good chemist. So it's always a pleasure to have Ange in the class. Right. Today's lesson, folks, is electroplating and copper purification. You can see one of my diagrams that I've already stolen. There we go. I'm not, I failed. Oh, Ange, don't be soft. That's not true. He did badly in one test, guys. Just ignore him. Ange, don't be coming in here and being all negative. Right, so electroplating and purification of copper. Learning objectives. Number 1, understand anode metal. And also the anode reaction. So I'm just going to flip my laptop over. I'm going to turn on my little fan. My little fan has to be on because my laptop overheats. There we go. So, understand the anode metal. I'm going to add an extension onto that. And the anode reaction. Yeah. And the anode equation. The equation is actually kind of more useful, really, than the actual understanding the reaction, because the equation will tell you what the reaction is, whether or not it be redox or whether or not it be reduction or oxidation. Have fun. Electrolysis is one of the best. It's one of the best. No cap. Have fun. I don't really know what no cap means. I'm very confused. Understand anode and electrolyte match. Yeah, I like it. And the last one is no copper purification. Okay. So the first thing I'm going to talk about today is going to be electroplating. I left this at the end of last lesson and moved that one way over there. Whoa, didn't mean to make it bigger. So last lesson we talked about this. We were talking about the idea that we could use electrolysis as a method. So electroplating. If you want to go online and find this diagram, please feel free. Just type in silver electroplating and it'll come up. Electroplating. A practical used to cover brackets plate. Yeah, cover one metal with another. Okay, so the example in this particular scenario is the fact that I've got a spoon, and that spoon is probably going to be iron. Now, the problem is no caps means no joke or no exaggeration. Thanks, Zina, for bringing me up to date into the world of the youthful, and the fact that apparently I have no understanding of your language now. I am very old. If you've seen all my grey hair, you'll understand. So we've got an iron spoon, and we know that the problem with iron, of iron is that it rusts. Is rusting. So what we like to do is we like to protect it. And one of the methods of protection is to cover in a metal that doesn't rust. So it might be zinc, it might be silver. Silver, of course, is for the posh people. Yeah, it could be chromium. Lots of different choices, but they tend to focus on the silver plating or copper plating. So I'm just going to mention, that's a nota bene. Most common plating, I'm going to stick to pink, I think. most common plating practicals involve either A, silver, or B, copper. There we go. So in this case, we're going to look at silver. Okay, so we've been doing electrolysis. I don't want to rush you guys. There you go. You can pause the video at that point if you want to make the notes. Please do. So far, what we've been doing in electrolysis is that we've been electrolyzing salt solutions. And the idea being to get out two products, at least two products. Yeah. So this is kind of a summary. This is just me doing a quick summary of what we've done so far. So far, we've done, summary so far of electrolysis. I want to make it really clear, you see. Number one, summary of electrolysis. Electrolysis of molten. Yeah. Now, what this is, brackets, something like NaCl liquid. We've taken an ionic compound and we've split it. That's what the word electrolysis means. To split ionic compounds using electricity. Now, when we do it on molten, we get sodium metal, and that is going to occur at the cathode because we have the cation. It's attracted to the negative electrode, panic, positive anode, negative cathode, where the electrode then gives it one electron to turn it back into sodium metal. It will come out as a liquid as well at that temperature. The next thing is we produce chlorine. Yeah, we produce chlorine gas. And the reason why is because the chloride ion is attracted to the positive electrode, which is the anode, positive anode. Yeah, those two, the electrons will be torn off it. It will become chlorine and two electrons. And those disappear up the electrode. Yeah, that's what's happening here. You know that this doesn't really appear in the equation. I'm just representing what the electrodes are doing. Yeah, this is the positive electrode, opposites attract, and it's going to take away the electrons. Yeah, it's just nice to mention it. Those don't really appear in the equations. That one does. The actual equation looks like this. There we go. I'll make that electron a bit bigger just for clarity. There we go. So we talked about molten. The next thing we did is we then talked about the electrolysis of solutions. Electrolysis of solutions, aqueous. Brackets, NaCl aqueous. This is brine, and they love brine. Love brine. Now, what we realized when we're doing solutions, we also covered the main ones that you need to know about is sodium chloride. You need to know sulfuric acid, dilute sulfuric acid. Yeah. And you also need to know that copper sulfate, aqueous. Cool. So those are the three you cover at GCSE. Now, what we realized in this is that when you do sodium chloride aqueous, you don't get sodium metal. What we get is we still have the chloride ion becoming chlorine and losing its electrons. Remember, oxidation is loss. That there is losing. Yeah, this is oxidation. Because it's coming out. And out means loss. It means product. Yeah? On the other side, we have the hydrogen ion gaining 2 electrons to form hydrogen gas. Now that one is gaining electrons. These ones are going in. That's red. Yeah, reduction is the gain of electrons. We love oil rig. Oil rig is so handy. Oil rig. So they're going in. And of course, gain has the word in it. And that's in is reactance. Yeah, so that's reduction. And then we get a byproduct of sodium hydroxide because they're left in solution. This is aqueous. And this is not a product of electrolysis. It is simply the byproduct of the electrolysis of sodium chloride solution. So we get three products. The three products we get are chlorine gas, which is a pale green chlorine gas. We get colorless hydrogen gas. Colorless hydrogen gas at that's a cation. It's going to go panic, positive anode, negative cathode. It's going to go to the negative cathode. So that's going to be going to the cathode. Yeah. And we get another byproduct of sodium hydroxide, which is an alkali, which is why I've labeled it purple. So then we did sulfuric acid. So then we did, so this is kind of a continuation of number 2. Yeah. So then we did sulfuric acid. Now in sulfuric acid, something similar happens. Yeah, we get hydrogen gas because of the 2 H pluses from the acid to forming H2. But now what we also get is oxygen gas. Because what we have is we have the OH minus forming oxygen. And I think that was water on that side, and there was something like 4 electrons on that side. And I think that now all adds up. And this ion happens, this is what happens because the SO4 2 minus doesn't get broken down. Yeah, not broken down. It's easier to remove the electron from the OH minus than it is to the sulfate. That's all you need to know. Yeah, and that's all you have to know from the electrolysis of sulfuric acid, aqueous. Then we did copper sulfate. Right, so we then did copper sulfate, CuSO4, aqueous. Once again, this time we have the copper 2 plus gaining the 2 electrons. And we form copper metal at the electron. Now this has an observation. So this happens, this is a cation, which will be attracted to the negative electrode, positive anode, negative cathode. So this is going to happen at the cathode. The cathode will turn pink due to being covered in copper metal. Copper solid, which is that. Yeah. Now, the reason why this reaction doesn't happen, this reaction here to form hydrogen gas doesn't happen. And the reason why is because copper, this is a nota bene, copper 2 plus gains the electrons due to being less reactive than hydrogen. We can link that to the electrolysis of salt water. Why does this guy gain it and the Na plus doesn't? Yeah, the alternative to that reaction there was to have the Na plus gain the electron and form sodium metal. That there doesn't happen. It doesn't happen because hydrogen is less reactive than sodium. I like to make my notes pretty. H plus gains electrons since hydrogen is less reactive, than sodium. So it gains more easily. We're done. So it's nice to do that. That brings us to a summary. Now what's going on with the electrolysis in terms of plating? So now something odd happens. So electroplating. Sorry, my letters are all different sizes. I'm going to zoom in. Electroplating. Okay, so if I want to use electricity, I've got an object, I've got myself a spoon. We know this game. I've got myself a teaspoon. Yeah, and it's made of iron, and I want to cover it in a metal. Yeah, this is going to rust. I want to cover it. So what I want to do is, the first thing I want to do is decide what metal I want to plate it in. We've got a couple of choices. Let's plate it in silver first. So, metal to plate is silver. Okay. So, in order to do that, I need to have silver ions. So, bullet point. So Ag1 plus cations are needed. So what I'm going to do is I'm going to put into this beaker an electrolyte. So this is the electrolyte. And we know that the electrolyte is a liquid that conducts a liquid or solution that conducts electricity. Well, if we want to conduct electricity, what we need is in red, I need capital letters, free moving ions. I need free moving ions. Now, if I want to plate in silver, then I'm going to choose an electrolyte with a silver ion. So the example you need to know is we need to know silver nitrate. So this is silver nitrate. Now, silver nitrate contains two ions. It contains Ag plus and NO3 minus. Got to know your ions, folks. Now, at this stage, what I now need to do is I need these silver, so metal to plate is silver, Ag plus needed. Right, the next bullet point is to say we need the Ag plus ions to be attracted to my spoon. What that means is I'm going to make it a particular charge. I want to attract that guy over to him. So what am I going to do? I'm going to make it the negative electrode. So this is now, the spoon is going to be the negative electrode. Negative electrode. Otherwise known as panic. Positive anode, nope, negative cathode. I'm going to make this the cathode. I love panic. So handy. Leave me alone. Anyway, so I'm going to make that the negative cathode. Next, now here's the really clever bit. Now, what we need to do is, so if I've got silver ions going towards that spoon, what reaction is going to happen? Let's zoom in. I'm going to get him down to there. Zoom, zoom. So what's going to happen? I'm going to move my silver nitrate over to here, just because it's just telling you what I've got in my electrolyte. Right, what's going to happen? what's going to happen, I want to be able to, and I want to make my notes pretty. That's better. So what's now going to happen is I've got my iron spoon, but my silver ions, my silver 1+ ions, are going to hit the electrode, and the electrode is going to give back the electron. And the silver ions are going to gain 1 electron and become silver metal and form on the surface. I'm going to form Ag metal. No longer Ag+, but Ag metal. And the spoon is going to turn silver. So is this oxidation or reduction? Oxidation is loss. Nope, that's not loss. That's gain. Yeah, it's going in. So this is reduction. So this here is reduction because they're going in. That's how you identify. I love oil rig. It's my favorite thing. Next, now here's the problem. What's going to happen at the other electrode? I need another electrode, but there's a problem. And that problem is going to be that the silver ions in solution are going to run out. I'm going to be taking all of those silver ions out of the solution and putting them onto the spoon. And eventually, the silver ions are going to run out. So I'm going to do a rather clever trick. I am going to put as my other electrode silver metal. Now, the reason why is because, so this is my second learning objective, guys. So understanding the anode metal and understanding the anode electrolyte match, these two go together. These two learning objectives are going together. Because what we want to do is, we want to put the silver ions back. Now, here's the cool thing. So here's your nota bene. Nota bene. If the metal, gotta be careful here, positive anode, negative cathode. Positive if the anode is made from the same metal as the ion in the electrolyte, the metal anode will release ions into the solution. Now, can I just point out, by the way, that into the solution, this isn't an entirely truthful statement. In reality, if you use a metal electrode here, if you use a metal anode, yeah, if you use a metal anode, what will happen is some of those ions will drop off and some of those atoms will become ions. So it doesn't need to be the same metal. However, we don't tend to use metal electrons. The only electrode we tend to choose, which is metal, is platinum. And platinum won't do that because it's so unreactive. It just won't hop off. So the two electrodes we tend to use are graphite for all of these. And we can do this as a quick, right? For all of these, the electrodes are either graphite, which is a non-metal, or platinum. We tend not to use platinum because it's so expensive, but you can. Now, those two won't drop off in ions, but if you use anything else, it will. So what this means is I'm going to use this. So I'm going to use a silver anode. I'm going to draw a bigger diagram. I'm going to try and zoom in as best I can. Here's what's happening. Silver bar. I've got a silver bar of metal. Yeah, going to make that Don't like that line. There we go. And I'm going to make that the positive electrode, and I'm going to attach my spoon onto the other. It's a terrible spoon. I apologize. I'll try that again if I can, if my laptop lets me. It's a terrible spoon. Right. I fill this with silver. So this is silver metal, and this is silver nitrate. And what's now going to happen is that the silver cations are going to wander over, and the silver cations are going to gain an electron to become silver metal. And the spoon will get bigger. The spoon will gain a layer of silver on the surface. And it'll actually get heavier. You can weigh it afterwards. Yeah. What's now going to happen is because we're using a metal electrode and they're the same metal, what's now going to happen is the metal atoms, as part of this, are going to lose their electrons and become silver ions. And those electrons now run up the electrode. They're pumped round the pump and back down there. So what you're doing is constantly replacing the silver in the solution. So at the anode, the silver atoms become silver ions and lose an electron. It's the reverse. And that's the summary. If you're ever going to do electroplating, you actually just have the reverse equation at the two electrodes. Let's have a look at copper. Let's imagine we do this scenario where I decide I want to plate my key. I want to plate my key in copper. I'm going to make the copper the negative electrode. Right. So the question is, what am I going to put in the beaker? I need an electrolyte that contains copper. I'm going to use copper sulfate, which is blue, by the way. Which is blue. Dark blue, too. I'm going to use copper sulfate. Now, inside that, I've got blue copper 2+, that's what makes it blue, and colorless sulfate ions. What electrode am I going to use there? The answer is, I'm going to choose copper metal. So what happens is the copper ions move over to here, and they will gain their electrons. They'll gain 2, because when it gains 2, it becomes neutral copper metal. It goes from being aqueous 2+ to copper solid, and it turns pink. Yeah, we end up with this pink layer on the surface of the key. Now on this side, the copper metal, because it's the same metal, it's going to hop off to replace them. And I'm going to have the copper metal losing 2 electrons and forming copper 2+ in the solution. So, and the clever thing is what now happens is that the key will get heavier. The key here will gain mass in the form of copper. And the copper electrode will lose mass. It will lose mass as copper moves into solution. So you'll actually get to see this. Now this ties in directly to the end of my lesson, my last learning objective, purifying copper. So by the way, pause the video, guys, if you want to make those notes. So we've covered the 2 types of electrolysis, electroplating that we need. So now what I'm going to do, just underline that, and I'm going to put purifying copper. So purifying copper. So we love copper metal. Copper metal is beautiful. Yeah, copper metal. A beautiful metal. Beautiful pink metal. Look at that. It's gorgeous stuff. And we use it for a whole load of different reasons and for different products. We use it for coins. Why do we use it for coins? So Uses of copper. Uses of copper. Number 1, coins. Now we use it for coins because it's shiny and it allows us to be able to tell certain coins apart. It's also because it adds value. It provides all metals have an inherent value, so having copper on it means it's going to have some kind of value. Now, don't get me wrong, it's not as valuable as silver and gold, but it has a value. So we use it for coins. However, we use low purity copper. Purity copper. Now, the reason for this is, by the way, if you're interested in how much, it's about 95%. 95% copper. And we actually only plate the surface as well. But that is actually surprisingly, it seems pure but it's actually not that pure. The other thing we tend to use copper for is we tend to use copper for pans. Pans and pipes. Pans and pipes. Let's have a look at that one. Now, the reason for this, there are the pipes. Here are the pipes. And then further down, I'm sure we're going to come across a pan soon. Where are my copper pans? There they are. Copper vessel. I prefer a proper copper pan. There we go. Copper pans. And one more. There you go. That's what I'm after. Copper pans. So why do we use it for copper pans? Why do we use the copper there? Yeah, we use it there because it's a good conductor. Yeah, good conductor of heat and electricity. Conductor of heat. Sorry, electricity makes no difference in this case. Good conductor of heat, and it's inert. Yeah, it's not poisonous. It's not going to react. Yeah, okay. Now, once again, the purity of this stuff is actually relatively low, similar to the coin. Low purity. Low purity, about 95%. Just to point out, by the way, that's actually usually a deliberate choice. The reason being is impurities mean that they are some form of an alloy. Yeah, low purity here. Low purity actually increases strength. Yeah, different atoms of different sizes, strength. Just to tell you why, that's because if you've got a pure metal, then the atoms are all in nice organized layers. Yeah, and those layers can slide. This is why metals can be shaped. If you add an impurity, the impurity are atoms of different sizes. And what that does is it disrupts the layers. Yeah? Different size atoms disrupt the layers. Disrupt layers, and layers can't slide as easily. Okay, so when do we need copper, which is better than this? The answer is our third use, electrical wires. So we use electrical wires. So we use copper everywhere in wires. Let's have a look. Just gonna go scroll back to the top. Copper metal wires. There we go. So we use copper metal. It's in your headphones. They're in your iPods. They're in your iPhones. I know iPods are old, aren't I? I'm an old person. Yeah, but we use copper because it is a fantastic conductor of electricity. Fantastic. There aren't many metals that beat it. The best conductor of electricity is silver, but silver's way too expensive and way too soft. So we use it in electrical wires. However, we need to have, by the way, we do that because it's a great conductor of electricity. But the problem is we need high purity. The lower the purity, the worse the conductivity. So we need 99.98%. You can't get 100. 100 doesn't really exist. So this is now high purity. So how do you purify copper? High purity. Okay, so how do you purify copper? The answer is electroplating. So here's what you do. Here's what you do. Zoom, zoom. Right. What you do is you've got two pieces of copper. You've got a piece of copper here. I'm going to actually try and color code this. You've got a pure piece of copper wire, a thin amount of copper. What you're going to do is then you're going to attach that to the negative electrode. And then on the other side, you're going to add your impure copper. So over here, let's do some labels. Over here, we've got pure copper. Pure copper. 99.98%. Yeah, and on this side, we've got impure copper. Impure copper, usually about anywhere between 85% to 95% copper. Right, now for us to be able to use it for wires, we need pure copper. So what we now do is we make this one here is going to be the cathode. Panic, positive anode, negative cathode. And we're going to choose an electrolyte. The electrolyte we're going to choose is copper sulfate. And what that does is it puts copper 2 plus ions into the solution and SO4 2 minus ions into the solution, which do nothing. These never do anything. I'm just going to put them out the way. They just swim around happy as Larry. Now what's going to happen is the copper 2 plus ions are going to go over to here, and we're going to plate the pure copper with more pure copper. So it's actually going to get thicker. We're going to plate this with more copper. It's going to get thicker. We're going to plate this with pure copper because the copper ions, the equation is that, I'm going to move that again. I do love having a tablet. It does allow me to do all lots of clever things like that. So what's going to happen here is that the blue copper ions, the blue copper 2 plus ions, are going to gain their electrons, gain 2 electrons at this electrode, and turn into pink copper metal. And it's going to gain mass. Now on this side, the impure copper metal, with all of their, usually, by the way, carbon impurities, most common impurity, yeah, or sand, that's also another one. What's going to happen is the copper metal solid atoms are going to hop off that copper metal, and they're going to become blue copper 2 plus ions. It's nice of me to try and color code this as best I can. What's the equation? The equation is going to be that, changing my color all the time. So I've got, get rid of that. The Cu metal is going to lose its electrons because the electrolysis is going to rip them off, and it's going to become the Cu2 plus ion in solution, and its 2 electrons are given away up the wire, plus 2 electrons. And this is going to get eaten away. Yeah, it's going to get eaten. It's going to lose mass. And what you'll also form at the bottom is commonly referred to, this down here, this black stuff at the bottom here, is called anode sludge. Yeah, because it's going to just lose all of these impurities that aren't going through the electrolysis. This is called anode sludge. And sludge, anode sludge. Doesn't look like sludge to me. And these are all the impurities. All impurities in the copper. Impurities. So it's a rather clever process. The copper just literally gets moved to the other side. The impure copper gets eaten away and loses mass, and the impurities go to the bottom, and the pure cathode increases in size, and it never stops because you're constantly replacing the electrolyte ions from the anode. It's a rather clever process. It is actually an identical process to what we're doing with the plating. We're just looking at it from a very specific copper perspective. So that actually brings me to the end, copper purification. It's just nice to show you this over here. So the pure copper has been, the pure copper has grown. Yeah, you can clearly see it's grown, swollen down here. Yeah, but the other guy is being eaten away, and the impurities are appearing at the sludge at the anode. But it never runs out of ions in the solution because the anode is always replacing it. And that brings us to the end of electrolysis, finally. I know it's tough. I will post the questions on the classroom for you to do, just so you can see them. They're not overly complicated. Learning this is relatively straightforward, but I know it's tough, and I'll end the lesson there today. I've got 4 minutes, and it's break time. No, I'll leave it there. I'll go through some questions next lesson. I will. See if I can bring this back to my stream. There we go. Right, guys, I hope you found it useful. That brings us to the end of electrolysis. It is one of the hardest topics at GCSE. It doesn't even get retaught at A-level. This is tough. Once you do some questions, it'll be fine. You're going to have boatloads of example questions on electrolysis to do over the holidays with the mark scheme. Remember, one question, then mark it immediately. Do the complete question, mark it, make your corrections. Do the next one, make the corrections. Do the next one. By the time you get to question 5, you're a god. Yeah? Bye, guys. I'll see you all soon. Have a great rest of your day, and I'll see you tomorrow. See you later, guys.